Hi, my name is Jessica Rudd. I'm a PhD student at Kennesaw State University, so I'm really excited to be going after the sports talk and moving back to academia. I hope you're as excited as I am. I will say the only sports that are in my talk are the fact that I'm still recovering from having lost my voice at the Atlanta United game on Wednesday night. 7-0, yeah. The stadium is awesome, by the way. So if that comes across, I apologize in advance. A little more context, excuse me, about my background that's relevant is I spent 7 years working at the Centers for Disease Control and Prevention here, that's based here in Atlanta. So I do have a passion about public health. And, but unfortunately, at least in the group that I work at CDC, a lot of what we work on in public health is really still looking at traditional use of logistic regression, survival analysis. I think I might have seen one person in the room who has a CDC badge, but machine learning isn't really something that's a conversation that many people are having at the agency. But the great thing about being a PhD student is that you can ask any question you want as long as it's publishable and it gets you invited to conferences. So that's why I'm here today. So just a quick overview. I won't lecture at you about support vector machines because I'm sure people know what those are. The importance of disease classification question in this context, how SVM is applied, how some graph theory metrics can be used as features in a predictive model, a social network simulation, the initial results of this exploratory research that I'm doing, and really the exciting part for me is what this research has led to in the future for me. So really the take-home point I want to get from this slide is that the great thing about support vector machines that I'm sure many people in this room know is that it's a model-free algorithm. So a lot of the survey data that we use at CDC, I'm given surveys that are very wide, very high dimensional, not very long, often very sparse because variables change in the middle of projects, and still expected to do a logistic regression analysis, which is really difficult with that kind of data. But support vector machine is known to be just, since it's model-free, a lot more useful in that context. So I was really excited to see how can we use this algorithm for more improved disease classification to see what people are at risk for certain diseases in an improved way. So why disease classification? In particular, for this study, I looked at diabetes. Diabetes affects almost 30 million people in this country. 57 million of those people have prediabetes, and a third of the 30 million people in the US with diabetes are unaware that they even have the disease. So how do we change this? How can we have a predictive model that doesn't rely on somebody actually going to their doctor, having blood work done? Maybe somebody can just, in their phone, put a couple of facts about themselves and can find out what their likelihood of disease is and start the process of changing lifestyle, which is the way that you can prevent and improve your current diabetes status. So we're really looking at getting early screening and improved prediction for people to use that is non-invasive. So through previous research, SVM has been used, particularly for this question, for successfully with diabetes classification using several different data sets. It's comparable or even improved performance. In particular, this is a UCI machine learning data set, the PIMA India data set that some people may be familiar with, that in their test data set came up with pretty high accuracy. For some of you, it might not seem high. For health sphere, these are actually very good results and perform better than the logistic regression using the same data set. So that was something consistent that I found in the literature. Now, in addition, I was really interested in looking at, well, how would graph metrics be useful as potential predictors for disease? And the reason I thought of this is that even in chronic disease research, there is this idea that chronic diseases can spread virally, in a sense that your social network can affect your likelihood of certain diseases. So for example, the majority of my social network in Atlanta are long-distance runners. So our disease outcomes within my group is probably different than looking at the general population or other groups of people. So how would that matter? The research that I found was mostly in neurodegenerative disease research, so particularly outcomes of Alzheimer's and multiple sclerosis, where they actually used brain scans to create graph nodes and edges between sections of the brain, and then use those graph metrics as actual features in predictive models. This was really kind of impressive research. In fact, in one that was looking at classification of multiple sclerosis patients, even just using one graph metric from this study had accuracy almost 90%. So that's an extremely powerful take-home point. But for me, I want to know, can this be used in survey data? And so at CDC, one of our more popular CDC-led survey data sets is something called BARFIS. It's government. We don't have great acronyms. Apologies. It's a phone and cell-based survey of households in the United States, looking at different disease features, behavioral outcomes. And so using using the known conceptual model of diabetes, I used this data set to build a model. But I really wanted to know, can, in application, graph metrics be pulled from this? Now, unfortunately, there was no available data set of graph metrics in this way. But I'm really stubborn. And I'm also a trained improviser. So I decided to improvise and create my own social network. And I'm sorry, my throat is killing me. Time out. So naturally, because I'm stubborn, I created my own social network to attach to this data set. And I did so using the Watch-Strogat Small World network model. This is a based off of a lattice network, and it uses rewiring probabilities to create kind of natural clusters within a network that simulate, as close as possible, a typical social network. There's a lot of social network research out there in terms of simulating kind of common human social networks. They all have their pros and cons, but this one was relatively easy to reproduce for this research and to kind of add as edges and nodes into the existing data, and so that's why I used it. I used the R package to create this, and just so you know, every edge can only be rewired up to once, so even though the algorithm, you can set the rewiring probability even to 100% for every node, you're not going to get back to the lattice network because you can only switch each edge up to one time. Again, I used the R package to do this. And there's my pretty network after the fact. Now, here's the surprising thing. I used SAS to do this project. I know, horrifying. And one of the reasons why I did this, there's several reasons why I did this. One is that SAS is paying me to go to their conference next week to present this research. And again, I'm a PhD student. The second reason is really all about knowing your customer. Coming from public health and the CDC, SAS is still the industry standard. The algorithms that are in the package are statistically verified. Our doctors and researchers, scientists generally trust what comes out of the package. We do have R and Python working groups at the CDC, but in comparison to the 20,000 person workforce, it's still really small. And again, our machine learning capabilities are kind of very infant. So if I go to my team lead and tell him I've done this whole awesome research project in Python or in R, he's going to look at me and say, reproduce it in SAS, because that's what people want to see, and it's still what people understand. And so they have the OPTGRAPH procedure for creating some centralized graph metrics. And then I think I got things out of order. These are, I did the logistic regression as the grand model. And the outcome variables that were significant were really what would be expected from previous research: age, education, BMI, hypertension, cholesterol. And adding in the graph metrics, again, this is a simulated network. I wasn't really expecting one to be particularly useful. I really was just looking at how this application would work in practice. And in fact, really what this represents, the closest centrality, since I weighted the edges in this network based on household size, it's really a factor of the household size in this particular study. But again, was relatively easy to implement, so given an actual social network in a data set, shows promising results. And again, consistent with previous research. SAS also has high performance procedures, so you can do support vector machines in SAS with cross-validation to test the parameters. Unfortunately, while SAS is statistically verified, because of that, it's really difficult to do kind of your own programming and customize it. When I go to DC to meet with them next week, we're going to talk a little bit more about how to do better grid search in this for some of the parameters, but it's not set up in a way that makes that readily kind of available. Our penalty from cross-validation, a penalty of 0.2 gave us the best accuracy, and the polynomial kernel also performed the best. Linear and RBF, as kind of expected with this sort of data, had completely flatlined. And some of this has to do with, again, this is a first pass. The training data needs to be trained better, and once I do some of the grid search, that some of these parameters can be trained and regularized to get better results. However, it is promising that the SVM results perform similarly to the standard logistic regression. Given a larger data set, even more high-dimensional data, this could potentially be even improved. And you can see kind of where the linear kernel flatlines. And also the validation data set kind of suffered, so some training is definitely needed. Again, this is with the graph metrics included in the model, and this is without. So as expected, not much difference here in kind of this test scenario. What I'm really interested in, though, in the future, now that I've sort of looked at where we've started at, is how we can customize the kernel for the support vector machine. And so the first pass, we're working on doing a customized, our own written customized kernel, at this time in Python. But the future, which is really cool, is doing kind of this two-step deep learning process developed by one of my classmates and a professor at Kennesaw. We're actually going to use a neural net to learn the kernel and then apply the learned kernel into the support vector machine. They've already applied this in some pending research, publication research with extremely good results. So we're trying to apply it into different contexts, and this is one area that we're really excited about in the future. So again, all this is posted online. I am not hiring, but you can hire me. And considering I'm from New York and speak very fast, I have plenty of time left. So thank you.